Perfect. Thank you very much. Can you see my screen? I hope yes.
Yes.
Fantastic. All right. So thank you very much, Alvaro, for the kind invitation to this hands-on session for AI for chemistry and materials. Today, as you said, I'm going to be talking a little bit about machine learning force fields in the context of heterogeneous catalysis. So I'll start off with a quick background on both those areas. So really mentioning why heterogeneous catalysis in particular is an area where we're going to see big changes due to these new tools that significantly reduce the computational costs of in silico investigations. And then I'll move on to show some of the results that we developed when investigating these systems with our tools. I'll mainly be talking about how using machine learned force fields now has become very transferable and also easy to adopt for the wider community because of automatic training protocols using active learning. So I'll focus a lot on that as this is a hands-on session. And then I'll also talk about all of the interesting kind of science questions we can now answer with a cheap but accurate sampling tool. So finding lower energy barriers and capturing finite temperature effects with large sampling. And then at the end, I'll also go through a Jupyter notebook where we will see directly what it means to train one of the state-of-the-art force fields, the MACE architecture. We'll talk about active learning and also show how to get accurate absorption energies. So do global minima searching and getting energy barriers with these tools. And with that, let's get started. So, of course, heterogeneous catalysis is a question that has been extremely interesting for the community for a long time, simply because it's so atomistic in nature. And there's been a lot of progress in helping experiment through computational tools. And I think a good place to start is this famous volcano plot. So what these volcano plots are trying to show is that illustrate as the Sabatier principle, the fact that a good catalyst is one that binds quite strongly to a surface such that reactions can occur, that bonds can break, but at the same time doesn't bind too strongly such that the product can escape the surface at the end and doesn't end up crowding the surface and poisoning it. So the idea is that there's this kind of sweet spot where the absorption energy is perfect for a given catalytic reaction. And so how does that help us understand catalytic mechanisms, understand or help find new catalysts? Well, the idea is that what you do is you look at you try a few catalysts, you see where they lie on the single descriptor, the absorption energy, and you find where the sweet spot for your specific reaction of interest lies. And then you computationally screen a bunch of surfaces with your tools and find new catalysts that lie within the sweet spot, and then you can recommend those for experimental investigation. And of course, this is a very simplistic model or understanding of how catalysis works, but has been extremely efficient at helping discover new materials for catalysis. And there's a lot of underlying approximations that are made in this model. One of the key ones here are these scaling relations. And scaling relations show that there's an empirical observation that the absorption energy is linearly related with the barrier height of a reaction. And so you can, from an absorption energy, which is a very simple calculation, infer the height of the energy barrier, and then also, therefore, the rate of a given catalytic reaction step. And that's what's underlying these principles. But of course, the rate depends exponentially on that barrier height. And so we might actually want a much more accurate value for that barrier height. And in that case, we have to do a proper transition state search. And this is where we get into the realm where computation does become much more expensive. Another reason we might want to do a transition state search is that actually we want to break these scaling relationships. So a perfect catalyst is one, of course, where the barrier is low. We're trying to reduce that barrier. But at the same time, you actually want delta H to be high such that the products can escape the surface. And so if we want to, by making these assumptions, these scaling relations assumptions, we're actually missing out on all of the catalysts that we want to discover. For example, single atom alloys, where we can actually break this scaling relationship. And doing transition state searches and finding transition state activation energies is also routinely done with DFT, although more expensive for individual reaction steps. And this is another approximation of that volcano plot I showed earlier, that there's one key reaction step that we know a priori determines the entire, is rate limiting, and therefore determines the entire reaction rate. But of course, like in the gas phase, we have a complicated reaction network that has many individual reaction steps. And so what we'd actually have to do is calculate many of these transition states. And here we go in the realm of, hundreds of thousands of transition states. And that's where the DFT really becomes a bottleneck. The computational expense just becomes too much. And that's why we need to look for alternatives that are yet very accurate, because, as mentioned previously, the accuracy of this barrier height is paramount. Another problem is that often the potential energy surface is very complex. And to get an accurate barrier height, you need to be sure that you're really describing true global minima in your potential energy surface. So you need a lot of sampling. What about the surface? So here I've shown this very simplified surface, but in reality, of course, catalysis happens at vacancies, at step edges, at edges. So the simplified illustration of something that's quite computationally efficient to simulate the simplified surface is not really what's actually occurring experimentally. And so we see a lot of discrepancy in what we can do in silico with DFT because of these limitations. Other factors include finite temperature. What about molecules interacting with other molecules on top of a surface? Maybe we're interested in some excited state chemistry. And there's a bunch of other things that really make it difficult to relate this simplified model to what's happening truly experimentally. And these are all areas that machine learning force fields are being used and are key to tackle these problems, whilst not compensating on the true accuracy. And so I figured it might make sense to give a quick background on machine learning force field. That's not the main aim of this presentation, but the idea is, right, that we kind of have a very, very nice ladder. And of course, there's a lot of things, a lot of methods that I'm missing here, but right down from, solving the Schrödinger equation to approximations to solving the Schrödinger equation, like density functional theory, which is commonly used. We have this kind of ladder of what we can do computationally, and the more unprecise we get, so the higher the error, the more computationally, the less computation expensive we become, and we can simulate bigger and systems for longer times. And there's really a clear cut here where we're starting off with something that is ab initio, so just from from physical laws, to then kind of empirical force fields that parameterize, and we try to adjust such that we can reproduce experimental observations. So there's a clear cut here, and we can see that in the accuracy, but also in the kind of computational in the kind of systems we can simulate computationally. And machine learning force fields are the bridge here. What they promise is a way to get the accuracy of some of these ab initio methods at a cost that's close to that of empirical force fields. And so the idea is that you train on a representative structure, sets of structures with energies and forces on the nuclei, and you now train a machine learning force field. So you've got this energy landscape in position space, and you train a machine learning method to predict energy and forces on your atoms, given their position in 3D space. And so you completely circumvent solving the electronic structure of a configuration, which is what you would have to do with DFT, and directly predict the energies and forces on atoms, and can then run molecular dynamics. You can run enhanced sampling methods like umbrella sampling, so on and so forth. And so the machine learning method is one that has a bunch of training data that contains the energies and forces on configurations. The machine learning method translates that to some sort of representation of the atomic environment. And there's been a lot of progress in what these representations look like. And then you can do a regression and you can learn the energies from these representations. And then you get something that gives you near ab initio accuracy at a fraction of the cost. And if you do this locality approximation where you say that the total energy is the sum of individual atom energies, and the atom energies are solely defined by its neighborhood within a certain cutoff, then you also get linear scaling. And so that means that, we can say it's 100 times faster, but really the scaling is different. So the bigger the system, the bigger the difference in computational costs. So easily for big systems, we're talking 10 to the 6, 10 to the 9 times more expensive if we were to do calculate the energies and forces using electronic structure methods. And one of the key things is that these representations that I talked about earlier need to respect the symmetries that are inherent in our physical world. So rotations, translations, and there's rotations and there's been a lot of progress in developing methods all the way back from the kind of gap in Villa-Parinello potentials that used SOAP descriptors to more advanced descriptors such as ACE, all the way to now a more machine learning era where we introduce message passing, or where message passing has really established itself as a state of the art. So the current state of the art machine learned force fields are really using equivariant many-body message passing neural networks. And if you're interested in the development of these, then I've quickly noted down here some of these, the sources, the papers that introduce these methods. But key for this presentation is really that we have a method that gives us almost the same accuracy at a fraction of the cost. And so if we now go back to all of our issues, we can nicely see how these kind of tools are going to be critical in tackling some of these issues I mentioned earlier. And like I say, they're really being used for all of these things, but I'm going to just focus on a few. So talking about the fact that the surface is actually very different from this idealized surface, there's a very cool paper published by the Carsten Reuters group at the FHI in Berlin, where they looked at just iridium oxide surface. They simulated annealing. So they did some simulated annealing where you heat up the surface and then cool it down and geometry optimize. And they found this new surface structure. And this was very surprising to them because previously, this is not the surface at all that's been investigated extensively with computational methods. People have been looking at the surface for these surfaces for a long time, doing expensive transition state searches. But in reality, they actually found that the surface looks very different. And initially, they didn't. I mean, Carsten Reuters, of course, tells the story much nicer, but they didn't necessarily believe their model initially until later. An experimental group actually said, you know what, we've actually observed the same thing experimentally. And so this is a very cool illustration of how machine learning methods really bridge this gap from ab initio to experiment. If you were to train or adjust an empirical force field to replicate experiment, then you lose this predictive ability. Here we have a tool that goes from ab initio methods from quantum chemistry and can be used as a predictive tool to showcase and discover new things about our surfaces. And so the key takeaway here is that whatever you do afterwards with the surface, if you're looking at a surface that's not experimentally relevant at all, then all of the detailed barriers that you calculate of your reactions on top of the surface are rather meaningless. So It's really important to get these complicated surfaces correct. Another big problem, of course, is that there's such a variety in the materials that can be catalysts. And one famous project that's trying to address this challenge is the Open Catalysis project, where they've created a large database of configurations where the idea is that an accurate machine learning force field trained on these can then help you predict on almost any surface that you may be interested in. And so as you can see, there's really many approaches and many things where people are starting to use these methods. And what we're going to focus on today is really getting accurate energy barriers. And then I'll also show some cool results relating to finite temperature sampling and calculating free energy barriers. And so with that, let's get started. So our main aim in this investigation was to make machine learning force fields very accessible to the wider in silico catalysis community. And so ensuring that we don't just create a force field for a specific reaction, but much rather that we create a protocol that people can follow in order to create these force fields for a specific catalyst accurately, quickly, without much handcrafting and knowledge of the general machine learning force field training strategies. And so what we did is we looked at a reaction that's quite complicated. So indium oxide surface, adding the complexity, a vacancy in the indium oxide. And we looked at the entire reaction pathway all the way from CO2 to methanol. So CO2 hydrogenation to methanol, there's 10 intermediates, 5 distinct reactions. So relatively complicated. And we wanted to see, can we create kind of an automatic training protocol that can really be used to train a force field. And so the idea is we start off with just the material that we want from the materials project database. So in our case, indium oxide. And then you tell us what you think are the possible intermediates. And what we can then give you is a force field that gets you accurate absorption energies and also accurate barriers for each reaction step along the reaction. And with that, I'd like to talk a little bit about active learning in the context of these force fields and how we train these potentials and how to make them automatic. So you have a training set with DFT, calculated energies and forces. You train a machine learning force field, and now you can run a simulation very cheaply. So you run a simulation, be that MD, geometry optimization, so on and so forth. And from that simulation, you select a snapshot, you calculate a new DFT calculation, you add it through this training set, and you repeat this process. So that seems all very clear and good, but the question is, how do you select a snapshot from the simulation? And here it's become very important to have models that can tell you when their predictions are not so certain. So have an uncertainty estimate. And in the case of linear models and Gaussian process regression, we have an analytical expression for the uncertainty of our predictions. And in neural networks, the simplest technique of predicting an error is training many models and then looking at the disagreement of a committee of models. And so the project results that I'm going to present today were done using Gaussian process regression, using the GAP framework, but later we're going to be using a more up-to-date, more state-of-the-art machine learning force field, MACE, the MACE architecture, and there we're going to be making use of these committees. So we have an uncertainty, and for example, if I show you a simulation of a potential that hasn't seen many molecules before, you can see that it's not very good. But what the uncertainty helps us with is that we can immediately see when our machine learning force field is encountering a configuration that it hasn't seen before. So this is a bad machine learning force field that doesn't have basically no training data, including molecules. And of course, it fails. But what's nice is with the uncertainty estimate, we can nicely see where this fails. So here we see the uncertainty as a function of time, and we can see a sharp increase as soon as we reach this unphysical or unchemical phase space. And it makes it very simple to sample a configuration once it breaches this threshold. And so that's what we use for training our machine learned force fields in a kind of hands-off way. So now we have a way of obtaining new configurations. We run DFT and retrain the machine learned force field. And then on top of that, we also add another criteria. So we also, to make this whole thing completely automatic, we also need to know when we stop sampling, when are we happy with our potential. And what we can do is we can look at the sampled configuration when our machine learning method has finished and see whether that, and add some requirements on that. And in the case of geometry optimization to get accurate adsorption energies, for example, we can just check whether the sample configuration from our machine learning method is actually a DFT minimum. And so if the force is the maximum force on our DFT evaluation of the sample configuration is below a given threshold, then we can be sure that our machine learning method has actually learned some relevant adsorption structures. And so what we do is we train a machine learning method step by step, starting from bulk, fitting the oxygen vacancies, adding some molecules, adding some more molecules, geometry optimizing them, and then finding barriers using nudge elastic band searching. So then in the end, what we get here is a nice piece together of getting from carbon dioxide all the way to methanol, getting all the barriers of a suggested reaction pathway. So that was very qualitatively, at least this video here. What does this actually mean in terms of barrier heights and energy? So this is the DFT ground truth. And if we converge our machine learning force field in the way that I talked about earlier, then we can see that our machine learning force field can really capture this whole variety of all of these different adsorbits and structures accurately, although we have a complicated oxide surface. So this is, of course, very nice, but more than that, we can now use our cheap method to try and find alternative reaction pathways, to find alternative adsorption sites, and maybe also look at some finite temperature effects, things that we couldn't do beforehand. And so that's what I'm going to talk about now. You can see that here we've found a pathway where we significantly reduce the barrier height. So that's the first thing I'm going to talk about. And then also a bit about finite temperature sampling. And so the key in optimizing paths is that now we have a tool where we can explore and use our chemical intuition to explore the surface well. And in fact, here, our automatic protocol, where we look at different possible paths, even without any chemical intuition or input from a user, found a lower barrier. And this initially, when I saw this, I was actually a bit skeptical, or I was disappointed that it didn't find the true barrier height until I realized that actually this is just a lower barrier, and it's revealing something that previously in literature just wasn't seen. So here you can see that this is the path in literature, and the adsorbent has to move out of the oxygen vacancy that's indicated by a cross here, and in the path that the automatic protocol found, the adsorbent can remain in this oxygen vacancy, which is the active site, throughout the entire path. And so if you look at this from doing umbrella sampling or any kind of thermal, and looking at any free energy barriers, then you will of course find that the reaction progression is exactly via this route here. And so we found a significant decrease in the barrier height just by being able to sample different possible reaction pathways on top of the surface. And similarly for the next step, so we then continued on and looked at the next step. And what we find is that actually the active site, which was previously thought to be this indium oxide that has 4 oxygens around it, so it's 4 oxygen coordinated, is actually not the active site at all, but the reaction, although looking very similar, actually occurs on a different indium that is 3-fold oxygen coordinated. And so by searching for various minima on top of the surface, we find this lower barrier. And so actually we find that this reaction step has a higher barrier because the minima that were proposed in literature are actually not thermodynamically relevant. And if we do some, so these are the two paths. Here's the first one, here's the second one. And if we do some finite temperature, so if we do some umbrella sampling, we immediately see that the reaction progression is actually along this path here, the true minimum energy path, and it spends virtually no time in this barrier that is just between two local minima in the potential energy surface that have no relevance to the actual reaction progression. And so what we wanted to see is whether the existence of these minima that are elusive or to previous studies, if that is just coincidence or if there's a more systematic kind of existence of these complicated potential energy surfaces. And so we ran some global minima searching with this minima hopping algorithm where you alternate MD and geometry optimization, and you can find new minima in this energy landscape. And here we've plotted all the possible minima for carbon dioxide on top of the surface, showing the different energies. And so you can see that some have negative absorption energies and some have positive, but these are all local minima in the potential energy landscape. And just to make sure, these are actually minima also in the true DFT potential energy surface. We sub-selected a few of them and ran some expensive DFT optimization. And so what that means is that, firstly, if you minimize a single configuration and take that as your absorption energy, then you might get stuck in a high energy minimum that has nothing to do with the thermodynamically relevant absorption energy that you would need to do any sort of catalytic screening or whatever. And secondly, it means that you need a very accurate and much faster method in order to do this extensive sampling. And with that, I would like to wrap up kind of the presentation part of this of this talk. We showed that these tools are going to be critical in tackling various challenges in heterogeneous catalysis, be it from capturing more realistic surfaces or capturing the large variety in possible materials that you can have that are catalytically active. In this specific talk, we showed how accurate energy barriers can be obtained in a way that requires very little knowledge of how to train machine learning force fields using these automatic active learning training strategies, and that can be very rewarding in terms of obtaining lower energy barriers, which are more thermodynamically relevant, and then also allow you to do some finite temperature sampling. I didn't mention this earlier, but the finite temperature sampling that you see in the green lines here, that takes around 6 million samples of the potential energy surface, of course, something that is far beyond the reach of typical DFT investigations. And with that, I'd firstly like to thank everyone that was involved in this paper before I continue on with the hands-on session. If you found any of that interesting, please do check out the paper where everything is detailed in much more excruciatingly. And do follow the Twitter handle if you're interested in any future developments. We have interesting things coming up where we also compare to experiment. So if you don't want to miss that, then please do follow. And yeah, so particularly I'd like to thank, of course, my supervisor Gabor Chani and everyone else involved. Edwin Fako, Sandeep De, and Ansgar Schäfer were pivotal from BASF in this whole investigation, and everyone in the group, of course, as well. That makes the whole experience very enjoyable, and all the funding from the computes and also the university. And so with that, I think it's a good time to move on to the hands-on session where I will go through a Jupyter notebook that I will make available after the session that shows what that shows in a hands-on way what I've been talking about just now. Just to give some credit, this tutorial is based on massively on the tutorial created by Elias and Yuan Magdo. They created this for a different system, but I basically adopted their thing. And if you want to look at their tutorial, it's already out. So you can scan this QR code if you want to follow along, or basically just see what it looks like. In the hands-on session, I would be showing you how to train a MACE model, how to perform some active learning, do some absorption state search, and also calculate barrier heights using NEBS, so a two-sided transition state search algorithm. And the thing we're going to be looking at is a hydrogen bond breaking from CH3 on top of a copper surface. So something very standard that everyone should be able to relate to. And to give some more credit, the method that's going to be used is MACE, which is was developed by Elias and David. And this is really state-of-the-art force field that uses many-body equivariant message passing to create very accurate and transferable force fields. All right, so with that, I'll stop sharing the screen and then share again when I have the Jupyter notebook open. Actually, one thing I forgot to mention, if anyone has any questions, please do say so. And maybe I should just go back to the summary page. But if anyone has a question, please shout out now, or maybe we just have a quick question session about the presentation part of this talk. All right. Okay, so if there's no questions, if there's any questions ever throughout this whole thing, please feel free to interrupt, especially during the hands-on session. So I'll quickly share my desktop now, my second desktop. I hope that's visible. You should be seeing a Jupyter notebook. Could someone just quickly tell me if they can see that?
Yeah, we can see that. Yeah,
Perfect.
now it's
Okay, great.
browsing.
Fantastic. Okay, so just before I start going with the Jupyter notebook, I thought it might be nice to show you where the code lives. So this is really the code base for the MACE framework. It tells you how to install it. It's now very smooth, a very smooth install process. And so just please go on GitHub and you can then easily download all the tools that we'll be using today. There's also an extensive documentation page here that gives you detail on how to train the force fields, how to install, and all of these things. And so with that, I'll move on to the notebook that I quickly prepared for this. So here you can see the structure again that we're going to be looking at today. And please do read through all of the details that are here. So, you know, the papers are linked and all of these things. If you have any questions later, obviously also drop me a message, but this notebook is really quite detailed. And so unfortunately, I wanted to run this all live, but I didn't get access to an interactive GPU. So I'm just gonna run things, but they've been pre-computed. So here, the first thing we do is, okay, we're just gonna import some basic things for plotting using the atomic simulation environment, very standard stuff. And so here is the first model that we're going to be training, and the training data is included in this notebook that you'll get access to later. And initially, we have a very small training set of 84 configurations. that are just kind of rattle configurations, a little bit of active learning, but not very much. And so if we want to have a look at that, yeah, maybe let's have a quick look at this. So the kind of structures that are included in this data set are methane on top of copper, and also some CH3. So that's kind of the structures that are in this training set. Small surface, just so that, you know, for this illustration, we want to keep the computational time of the DFT and everything quite low. So pretty standard stuff. And so this is where we come to training a MACE potential. Very obvious thing. So there's a run train Python script, which takes in various commands. Where's the training file located? Validation file. If you don't want to have a validation file, you can also split your training set size with a certain fraction. Another thing is that you can select the E0s. These are energies for each element. And so, for example, if you have 10 copper atoms, then it will subtract, before doing any fitting, 10 times the isolated atom energy of a copper atom. This makes the fitting easier. And if you have reactions or want to extrapolate to unseen reactions, then it's very useful to explicitly put these isolated atom energies into your training. But you can always use an average as a command, and it'll calculate some reasonable isolated atom energies for you on the fly. Some of the key parameters that are for the MACE model are the irreproducible representations of the hidden layer. Well, the hidden eReps here. So I didn't go into too much detail of how the MACE framework works, but the idea is that you expand the local density in a basis, and this basis has a certain body order, so it can be 2 body, 3 body, so on and so forth. Typically, MACE models are fit with correlation order 3, so that's a 4-body potential, which is another parameter. So correlation order is the how high the body order of your potential is. Then there are messages passed that contain the description of this many body environment, and this is what you specify how large these messages are. So in this case, we would have 128 channels, and we include an invariant. So L equals 0, that's what the 0 stands for. L equals 0 message, so a scalar, and also a vector. So that's this would be if you look at the paper, capital L equals 1 model. And so these are kind of the key parameters that you can train and choose. Another one is the spherical harmonic. So the angular part of the basis is expanded in spherical harmonics to making the basis rotationally equivariant easier. And here you can select the maximum L of the spherical harmonics, and so this kind of selects the angular resolution of your basis. Another key parameter is the radial cutoff, and so this determines how far your local energy, how much your local environment, how far your local environment can see, and so how much the local energy of an atom, of an individual atom, is determined by the density of the atoms around it. And so there's a bunch of other small parameters, but these you can really leave at their default values. And so here we've created a quick fit. This is a quick fit, so it's only 100 epochs long. Starting off with 50 epochs trained with an energy and force weighting of 20 and 1,000, because we're both including energies and forces in the loss function. We need to set which of the two we want to pay particular attention to. And so you can change these weights, and empirically it just works well to initially fit mainly on forces and later fit more equal on energies and forces. And so let's quickly run that. And so when we run this this command, this is the output we get. So it details everything, and if you ever need to debug or something, these are the kind of the log files that you would send to help understand if you have any problems. And so here we can, so here's all the details of the model parameters, and then here we can see what happens during training. And so of course I pre-ran this, but these lines would come out consecutively during training. And so you can see that the error reduces, and after a few epochs, we have a model that's quite nice. I tried to keep it small just so that, oops, it's truncated. Okay. The output is a bit longer, but it's almost finished here. Basically, it tells you the final errors at the bottom of this, but you can check this out once you have access to the notebook. And like I say, this is done a few epochs only because I wanted to reduce the computational cost of running this notebook. And with that, we can start running some molecular dynamics. So just some standard imports again. We're going to run Langevin dynamics. And so the idea is that we read in an atoms object, we define our MACE calculator, we set our calculator, and then we run some dynamics. And what I did previously is that not only did I train one force field, but I trained 4. And so now we can look at the uncertainty that I mentioned earlier by comparing the output of 4 different models. And so what I'm saying here is train all, run MD using all 4 models, and then it automatically saves the disagreement between those models. And so then we can run this, and so this will normally run, but again, because I don't have access to GPU, I did this beforehand. We can read in the results, and then have a look at the uncertainty. And so here, it's telling us, okay, we ran 2 picoseconds of MD simulation, and we can now have a look at what the uncertainty. So here I'm keeping track of the uncertainty in the forces. And so here you can see the uncertainty of the forces for each atom in the simulation cell. So let's have a quick look here in MD simulation at the simulation we ran. Move this over here. And so here this is the simulation that it ran. Looks pretty physical, methane on top of copper. And here you can see the uncertainty in the forces along a trajectory. And so if we set a very low, quite a conservative threshold, then we could maybe say, okay, we want to sample a configuration here at around 550 time step, and can add that into the training set after evaluating it with DFT, and so improve our model, like I mentioned in the presentation. And so now if we do this a few times, this kind of active learning, we get a very accurate machine learned force field that can get accurate energies. And one thing that we can do now is this minimal hopping. So trying to sample the adsorbate configurations on top of the surface by alternating molecular dynamics and geometry optimization. And this allows us to find minima that we previously might have missed with a single DFT geometry optimization. And so we now load the training set from a model after some active learning, and we see, okay, all right, this model has 328 configurations, so a few more, and then we run some minimal hopping. So just simple import minimal hopping. We read in the starting configuration. In this case, it's the same configuration, only that one of these hydrogen. No, actually, it's not. Well, I'll show in a second what we're simulating here. And then reading in a model again, creating the calculator, and then we just run some minimal hopping with this built-in method. Do 10 hops, and yeah, so we can run this, and then we can plot the results. And so here's the result from this minima hopping run. Well, I'll show what this graph means in a bit later, but here, let's move this over here again. Here you can see the trajectory. And so what it initially does is it geometry optimizes and finds a minimum. Then it runs some MD. So here's some MD, and then it geometry optimizes again. And in this case, it found the same minimum, but slightly lower. But that's artificial. You can see that it felt like it found the same one. So here we're seeing geometry optimization, MD run, geometry optimization, and we go so on and so forth. And so it kind of alternates between this minima, this geometry optimization and MD. And you can see that initially, the hydrogen was there, and it's found a new minimum over there. But actually, the minimum is higher, all the way up here. And so it goes back, and we find some new configurations. Also, this kind of configuration space is explored. And of course, you can run this a bit longer, and then maybe you'll get some more interesting kind of minima that have a bit of relevance. And so this is one of the cool things we can do with this cheaper method. And then maybe this is where things become even more interesting, is that we can do some transition state searching. In this case, we're going to show a nudge elastic band using the nudge elastic band method. And so this is a two-sided transition state search. So we have two minima, we connect it with a path, and then we minimize this path. And so that's what I talked earlier about in the presentation. So you have initial and final states. You connect them with this kind of elastic string, and then you geometry optimize the string. A few more details are here. And so let's just import all of the required tools for that. And the first thing we want to do is we want to optimize the start and end configuration. So we just quickly run that. And as you can see, okay, my start configuration I picked quite well. The end configuration, not so much, needed quite a few geometry optimization steps to find it. And again, this is just extremely cheap to do. This runs immediately. So again, I'm not running it live because I don't have a GPU, but if I would do this, it would take basically exactly as long to run this on an A100 as me showing this output here. So it's very, very quick. And then with these equipped with these two minima, we can now connect them with a path. So what we do is we say we want 7 images in between this path. We replicate them, linearly interpolate them, just as a simple way to approximate what the path could look like. So save them, and then geometry optimize this neb path, and optimize it until the maximum force is below 0.05. And once that's done, we've got a relatively accurate barrier. And if we read in the resulting path, we can have a look at the energetics. And so this is telling us, okay, this specific reaction, which entails this hydrogen that you can see here splitting off of this carbon, has a barrier of 1.5. Now, this is a potential that has never ever seen this kind of reaction before. So in the training data, it contains none of it. So in fact, it's actually quite impressive that it converges this neb calculation at all. And whether this is accurate or not is neither really here nor there, because what we now do is do some active learning where we add these configurations back into the training set and iterate until we're happy with the errors we're getting with a much reduced computational cost. And so, of course, you can see here that we didn't do any climbing neb images. So what you do now here maybe is, add a few more images, make sure that the transition state is actually on top of this barrier with some climbing neb, geometry optimization. But for the simplicity of this notebook, we're not gonna do this. But let's have a quick look at the path. So this is the path. Starting off with a geometry optimized structure, And then we can see this hydrogen splitting off and finding a local minimum. So this is the other local minimum, and then the net path just connects these two local minima and over the smallest barrier possible. And so that kind of takes us to the end of the hands-on session. What we quickly looked at is training a machine learning force field. So this MACE architecture, very simple to download, very simple to use. How you would go about doing some active learning, how you would find absorbent energies and structures using these computationally cheap tools. And lastly, how you would do some barrier calculations. And with that, thank you all for listening to this this quick hands-on session. I hope you took something away from it, and do let me know if you want access to this notebook, and if you have any questions, I would be very happy to answer them.